Okay, so hi everyone. So let's see this question. Probably this you can count in your aerodynamics or fluid mechanics. Okay, and the topic is dimensional analysis. Okay, all right. So a passenger aircraft cruising at an altitude of 10 kilometer. Okay, with the flight speed of 250 meter per second. At this altitude, the air density and temperatures are given 0.414 kg per meter cube and 223 Kelvin respectively. Okay, now they are saying a geometrically similar 1 raised to 5 scale down model of the aircraft is tested in the closed circuit wind tunnel. Okay, this is what they have given. Now don't say that sir our wind tunnel topic is removed from our syllabus. I know this is removed. The concept required to solve the question or operation related to the wind tunnel they will be not asking, but the wind tunnel is a construction of it consists of your steady nozzle and test section, right? So it is just variable area closed loop duct, right? So the testing part definitely we can do, okay, but the operation required to operate the wind tunnel, the equations required to operate the wind tunnel, they will not be asking, but the wind tunnels will be present. Don't blindly believe on the syllabus, they can ask the question. Okay, the test section pressure is maintained at a 1 bar, okay, or in Pascal, this much. Assume that air behaves as an ideal gas. This is given, we know that this is a universal value. If the wind tunnel test is to be achieved such that the lift and drag coefficients are same for the wind tunnel model and the actual airplane in the flight. Now this is a very important statement, if you can understand, and this is very important to solve our question also. Okay, we'll see this. The required wind tunnel conditions are, now they have given 4 options. Now the question is asking, now the first thing is question they are in the question they are comparing, they are saying that you compare two things. Okay, one is the actual model or actual prototype to be more precise, and one is the scaled down model, small version of it. We call it as a model, right? In fluid mechanics of dimensional analysis chapter, we call it as a model, and we call this actually it is a prototype. Okay, if you can recall. Now they are saying that please compare this, and they are saying that these two conditions, lift and drag coefficients, are same in these both the conditions. Okay, now they have given the few values, pressure, temperature, maybe all those things they have already given, velocity, density, and the temperature they have given. They are asking you to compute the, what is the value of velocity here in the wind tunnel for a model, for a small version model. What is the temperature, what is the density, they are asking you. Okay, I hope now the question is clear. The condition given this as a, your CD is equals to drag coefficient is equals to the lift coefficient and the same condition is applied for both the models or both the prototype and model. Okay, I hope now the question is clear to you. Now let's proceed to solve this question. Now I know this is a bit tricky. Okay, that is the reason I have taken this. This is not just straightforward. I in the few minutes we'll come to this why I have taken this question. Okay, so let's proceed for this. I hope now you understood properly what the question is asking. Okay, now now let's write the given data so it will be easy for us. Given data. Okay, we'll go slow, we'll try to understand each and everything, but in the exam you have to solve this very quickly. Okay, you already max 2 or 3 minutes assigned for each questions, right? Okay, so let's write this as a prototype, or let's call this as an actual model, actual version. Okay, not model, actual version, actual. Now your prototype is having the thermodynamic properties of velocity. This is so it is operating at close to the sonic value 250 meter per second. Okay, at a height of let's write h1. So now the important thing is I'll give suffix 1 to all the properties of prototype. Okay, now then we have the suffix as a 2 for our small scale down model. Scale down version of model. Okay, so I'll give suffix 1 for prototype, that is actual, and I'll give suffix 2 for the model, all the properties. Okay, so h1 and v1, it is, so height is 10 kilometer altitude, they already given this one. Okay, now the all other variables are your temperature and density. So density I'll give this as a rho 1, which is 0.414 kg per meter cube. Okay, and the temperature, which is 223 Kelvin. It has to be lesser than the sea level temperature, right? We know that, we have studied the atmosphere temperature. As we go to the 11 km altitude, the temperature decreases. Okay, now for the model, so this is the actual condition of your aircraft. Now the same as per the similarities, we'll do the scale down analysis and we'll have some properties related to that. So pressure they have given this as a, sorry, this is P2. Pressure they have given this as a 1 atm or 10 to the power 5 Newton per meter square. Or you, so this is very important. If you don't know the unit conversion now, then this can become difficult for you. Okay, so atm and 10 to the power 5 both are same. Okay, now they have given you the statement of a geometrically similar 1:5 scale down model of aircraft is tested. Meaning of it, that they have reduced the scale for a wind tunnel analysis in terms of 1:5. That means your L2 is greater, sorry, your L1 is greater than the L2. That means your actual prototype is the bigger than the model, and this makes sense also, right? You cannot put your whole aircraft, big actual aircraft, in the wind tunnel. That is not possible. And this is what we do the reduced model analysis in terms of the geometrically similarities. That in that case your L1 becomes greater than the L2. Now in that case you can write L1 is equals to L2, L1 raised to L2 is equals to 5. You can also write in, you can see also, you see in this way, L1 is equals to 5 times of L2. That means your L1 is 5 times of the L2, right? You can also see in this way, L2 divided by L1 divided by 5. So that means your L2 is smaller than the 5 times smaller than the L1. Okay, I hope this is clear. So generally students do mistakes here. If you will take L2 by L1 is equals to 5, then you will put that value in the equations, and then maybe the values, or not maybe, definitely your values will be wrong. Okay, it will comes out to be another value, smaller values. Okay, now I hope this is also clear. Okay, so these two values are given. I hope now you understood the question properly. Now they are asking you to compute the V2 or then T2, then the rho 2. These are the values they are asking you to compute. Now we'll go slow, we'll try to understand each and everything. Okay, now these values are from your test section. Okay, fine. So now listen this very properly. They have given that if the wind tunnel test is to be achieved such that the lift and drag coefficients are same for wind tunnel model in the aircraft, actual airplane in a flight. So this is a very important statement they have given. That means they are saying that your CD is equals to CL for both the cases. Same for both the cases. Same for both. That means for actual airplane and the small model. Okay, and if you do the dimensional analysis, if you have studied that, if you will do this, CL becomes your function of angle of attack, Mach number, and Reynolds number. Similarly, your CD also becomes the function of angle of attack, Mach number, and the Reynolds number. Okay, from here what we have understood? We have understood that when you have this condition, that means your CL and CD are function of angle of attack, Mach number, and the Reynolds number. That means it is indicating towards the similarities of the geometrically due to the alpha, and also due to the Reynolds number, and dynamically similar due to the Mach number. Okay, so from here we can conclude that our model and prototype are under the geometrical and dynamic similarity. Okay, I hope this is clear to you. Now from here I can conclude, if these two conditions are existing, I can happily write this equation. If you can, that the Reynolds number at any point on the surface will be same. Also due to the dynamic similarity, your Mach number at any point, any 2 points of the model and prototype will be same. Let's write M1 only. M1 and M2. I hope now this is clear to you. Now I hope it is very easy for you. We have one more hurdle. Let's see this. Okay, now we know these two conditions. This is fine, but now how we can put the values from the given data? That becomes difficult, right? Now that is the hurdle for us. Now let's do that also. So now let's proceed with this condition first. So we have Reynolds number similarities. So I can write, I hope you are aware of what is Reynolds number and how it is given in terms of equation. So it is just rho 1 V1 let's write C1. So this is C1 is the characteristic length for our aircraft. Okay, and all the other notations are usual. Then this the ratio of these two dynamic viscosity, rho 2, V2, C2, mu 2. Okay, all right. So now in your aerodynamics or fluid mechanics, you have probably studied, okay, that your dynamic viscosity of air or other ideal gases are approximated as the under root of temperature. That means your dynamic viscosity are function of the temperature. Okay, so you probably have seen the dynamic viscosity is proportional to the temperature. Okay, now if not, please mark this as a very important point. Okay, let me write that as well. Dynamic viscosity mu, let's say, of air or gases, to be precise, ideal gases, right, is approximated as under root of temperature. Okay, I hope this is clear to you. Now from here I can write this as a rho 1 V1 C1 under root of T1 is equals to rho 2 V2 C2 under root of T2. Okay, from here what I'll do now, everything is given to you. If you see, all right, so now you have these equation, you have arrived at this equation. You cannot proceed ahead because you don't have enough data. You don't have enough data to proceed ahead. Now you need to come to this, you need to use this condition, Mach number. So now Mach number can be written as, to proceed ahead we need to use this condition, and for that we know Mach number can be written as V12 under root of, sorry, that is V1 to A1 is equals to V2 to A2. Okay, again from this, sorry, we have speed of sound is equals to under root of gamma RT. From here onwards I can write V1 is equals to under root of T1 is equals to V2 of under root of T2. I can write this, right? Now you will come to know why I have wrote this, and this is what I was talking about, the hurdle part. Okay, if you don't know this, you cannot proceed ahead, you cannot arrive at this point. Now why I have used this condition, the reason is in this equation you don't know this ratio, even they are not provided in the question. So how you'll proceed ahead, that is the reason we have used this condition of dynamic similarities, and we'll use this ratio, I'll substitute here and we'll proceed ahead. Okay, if you do this, if you solve this, let's solve for V2 by under root of T2 because you have V1 and T1 values. So this can be written as 252. If you take under root of 2 to 3 value temperature, this will comes out to be 14.93, and solve this, you will come to you will get this as a 16.74. Please verify this value whether you are getting this or not. Now what we'll do, you have every values provided in the question. You have density, you have velocity, you have characteristic length in terms of C1 to C2, right? So this is also given, then T1 is also given, then this ratio is also given. Also we have got this, right? Now we can simply solve this equation for calculating the rho 2, right? So let's do this. So if you solve for rho 2, this can be easily solved by, let me do this. So this is density value, this is velocity value, velocity of aircraft. Okay, then you take C1 to C2, then you send into the left hand side, then this becomes 5 by 1. Okay, now you substitute all the values, this will be 223 under root of it and 16.74. okay, I hope this is clear to you. Now you can simply solve this, and this numerator I got this as 517.5, solved it, and the rho 2 I got this as a 2.07 kg per meter cube. Now please verify this value whether you are getting this or not. You must get this value. Okay, so rho 2 is, now we got the rho 2 value, which is 2.07 kg per meter cube. Okay, now what we'll do, now we'll use the equation of state, which is equals to P equals to rho RT, and for station number 2, not for station number 2, for model, for the scale down model I can write rho 2, P2, rho 2 and T2. Okay, so from here I can simply calculate the T2 because I already have the P2 provided, which is 1 atm, I know rho 2, I know R, which is for air, we can write this as a 287. Then this temperature we can simply calculate. So if you do that, and here it will have a density value. Then now the careful important point is that this pressure, this value must be in the SI unit. Otherwise, you will be getting different temperature. That will be wrong temperature. Okay, so don't substitute the value in ATM. You have to substitute in the SI unit, which is Newton per meter square. Okay, I hope this is clear. And the R value is 287. Solve this. Simplify this value, you will get temperature as 1. So it is approximated to 170 Kelvin. So please verify this value also. You are getting this, or if you are getting this or not, let me know. Now you can solve. Now the thing is, we have solved for density, we have solved for temperature, we just need to solve for velocity. How you will do this is very straightforward. Now you have this equation, you already have three unknowns. You can simply solve this, as simple as that. So you can write v2 by the root of t2, which is 16.74, I hope. Yes. So simply you know that temperature. Now you can simply calculate the velocity from here, and that will comes out to be 218 meter per second. So please verify this value as well. Okay, I hope now this is clear to you. You understood the procedure. Now the very important point was this one. If you don't know this, you cannot proceed ahead with the question. Okay, you cannot arrive at these values. So I hope now you understand the importance of this statement. If you don't know this as well, then that may become difficult for you. So dynamics, dimensional analysis topic requires more practice. Okay, you may get different kind of questions. Okay, different varieties of question. Not all the year they will be asking simply they will, most of the time what they do, they simply say that it is the Reynolds numbers are same for both the cases, prototype and model, or they say Mach numbers are same, right? So all the time they will not give you this statement. You need to, they maybe sometime they can make the difficult question that you need to understand they have given these two conditions. Okay, so this kind of question you can encounter in your exams, and option A was correct. Okay, so I hope this question make you slightly think out of the box. Okay, slightly new question. Okay, so let's meet in the next video. If you are having any doubt, please ask in the comment section. We will discuss that. Okay, so let's meet in the next video, guys. Bye bye.